Today's topic is going to be about surface preparation and photoresist adhesion. And again, with photoresist adhesion, for those of you who are familiar with it, this is the key mechanism that allows the photoresist to bond to the copper surface, whether it's an electroless copper surface, whether it's a bare laminate for inner layers. But this is the area where can be significant sources of yield loss, whether it's resist lifting, whether it's an open, a short, excessive undercut, etc. So we're going to talk about some of these and how we can enhance the photoresist adhesion so we can minimize or eliminate these types of sources of yield loss. So surface preparation, and this is, again, you'll hear this from me really throughout the troubleshooting process. A clean virgin copper surface is paramount in order to get good quality, whether it's plating, whether it's a circuitized inner layer or outer layer, or even just to get fine line, images, like 3 mil lines in spaces and below. You've got to have all the other aspects, of course, of imaging aligned, but surface preparation is the one I really want to concentrate here, because this is where I see a significant source of yield loss, not just in photoresist adhesion and photoresist process, but also in plating process, as you've heard in some of my other podcasts. So here, surface preparation is going to be the key. This is what's going to prepare the copper surface so the photoresist can easily adhere to the surface prior to going into the exposure process. Now, there's a number of ways to look at how the surface is really set to provide good adhesion. One of those is topography, micro roughening. You just can't see. Photoresists today have a different type of technology. They used to have significant amount of adhesion promoters in there, not so much anymore. So adhesion is really dependent more on how you prepare the surface, both mechanically, in other words, by roughening it up, and also by treating it chemically, and also enhancing the lamination of the resist in the lamination process to the surface. So I'm not going to go into a lot of issues here or discussions about profilometry, but suffice to say, you have to have some mechanism of mechanical adhesion, some micro roughening. It's very difficult to put photoresist and expect it to adhere over a completely smooth copper surface. And of course, the copper surface also has to be free and clear of other issues as well, such as residues, chromates, and we'll talk about that. But know that this is really key, as understanding the mean roughness of a surface and how to get there, whether it's mechanical preparation, pumice preparation, or chemical preparation, but more on that later. You can also, so I wanted to note though that if you have a surface that's very rough and very non-uniform, that's not going to help you with photoresist adhesion either. That's going to cause other problems such as undercut, potential etch outs, and opens in the circuit. And we'll talk about that very shortly. Now, what is the ideal surface? Ideal surface to get good photoresist adhesion, it's got to be clean, right? Clean virgin surface, oxide-free, moisture-free, no residues left on the surface. We talked about chromate removal. We're going to talk about that, how important it is. Chromate is what's put on the copper foil by the copper manufacturer to minimize or prevent oxidation when they ship you the copper. Well, that chromate's got to be removed. And where a lot of people make a mistake is they don't remove the chromate first prior to going into some of the other aspects of the surface preparation process, whether it be pumice scrub or other chemical cleaning. So I always recommend a first step, remove the chromate with an acidic mix of chemistry that then will give you a cleaner copper surface with some surfactants in there that you can remove some of the organic residues from the copper surface prior to going into the next step. And then it goes, how clean is clean? And there's not a lot of tests one can do, but my favorite is the water break test. And in the next slide, you will see that one of the things you can do is simply look at, does the water break and form up beads? I mean, think about this. You got a nice car, you go and you wax your car, give it a nice shine. And of course you want it because you want it to look nice. But what happens when it rains? The water beads up, right? In other words, it looks like this, which is what you want. That coating, that wax is protecting your paint job, from the outside elements. And the first thing you'll notice is that the water, when it hits the surface, beads up. Well, that's good for your car, but it's not good if you want a clean copper surface. If you get this type of situation here where after you think you've cleaned the board and then you dip it in water and it immediately beads up, and that means that surface is not clean. There's something still on it. What you really want to do is see this. You want the laminate, if it is clean, to be able to hold a sheet of water for 15 to 20 seconds before it breaks. And that's kind of it may be somewhat, simple, but, and again, it's a qualitative test, not a quantitative test, but at least it gives you some understanding of this, and it'll help you get over the hump of, is my surface clean or not? So here are some other surface contaminants that, besides the chromate conversion coating and oxidation, we have to worry about things like fingerprints, poor handling. And again, watch your operators, because this is going to cause you some situations here where you're not going to get good photoresist adhesion. You're going to get lifting, potentially undercut, and many other concerns. Here is oxidation, because again, either from poor rinsing or rinsing with too hot water, let the board sit. Keep in mind, rinse tanks are not holding tanks. You should be rinsing up to the proper amount of time with good, clean, deionized water, and then get the panels through the process and not wait and to the next step. And if it oxidizes, that means you're not drying the panels properly, or you're using poor quality water. And this is going to cause issues with potentially for resist lock-in, where you're going to get residues left on the surface and situations like that. Another one of my favorites is epoxy spots. They're basically resin being embedded onto the copper surface. And typically you see this in the interlayer fabrication side when the layers are being laid up into the lamination room. Basically, you get some pre-preg dust, basically epoxy dust that gets onto the panels. And epoxy, of course, is very difficult to remove if you don't know it's there. Typically, wet chemistry like microetchants don't help. You've got to go through some type of an oxidation material like either plasma or alkaline permanganate. But these epoxy spots can also prevent situations like photoresist adhesion, causing lifting, and other situations which will cause problems in a later situation in the fabrication process. Now, as we know, most of us, for the majority of us in the circuit board fabrication industry, we use what they call the subtractive process, where we basically build up the circuitry and then we remove the unwanted copper and photoresist that we don't need. The problem today is we're building much higher technology circuit boards, higher densities, finer lines and spaces. And we have the concern that as we go up into the higher technology realm of finer lines and spaces, we have to worry about the circuit geometry that we are leaving behind. Are we getting what we call excessive undercut? Are we getting too much copper removed during the etching process, which is part and parcel to the subtractive process? Another situation that we have to be very concerned with, of course, is what can exaggerate this is poor resist adhesion. If the photoresist isn't adhering properly, the exposed resist, that's going to cause more undercut and more lateral etch from the etching process. Now, the etching process does play a significant role in this, and in a future Take 5 podcast, we'll delve more into the mechanics and the chemical aspects of etching. But for today, we want to focus on the surface preparation and adhesion for the photoresist. So, to get good adhesion, what do we need to do? What do we need to do is, well, first of all, we don't want resist lifting. We want good conformance. It's about the resist conforming to the laminate surface and holding there during the various operations. We do want to ensure we avoid things like oxidation, poor rinsing, moisture, any handling issues, because scratching the copper foil, damaging it, scratching it, bending it, that's all going to potentially add into the equation for poor resist adhesion. In a future situation, we'll talk about the lamination pressures and temperatures. But again, short story here, excessive lamination pressures and temperatures and of course, too long of a hold time in the between lamination and then exposure can all lead to lack of adhesion of the photoresist to the surface. Here's a good example. You can see what this is, a schematic of, here you see your copper foil here, your layer. This is your copper, this is your laminate. Here is your hot roll laminator, both the top and bottom. These are your rollers. And this is your photoresist being applied to both sides through the process of hot roll lamination in the photoresist area. And you can see that it's very important that the photoresist conforms to the surface. Here's a little dent here. It's just showing you that with normal dents and scratches, you expect to have some situations like that, and you want to ensure that the photoresist does properly adhere. Because otherwise, if this is a significant dent and scratch like you see here, that's pretty deep. Good chance that the photoresist never actually makes contact with the copper, the surface all the way down here. And then what's going to happen during etching? The etching's going to come underneath here, and because it's an area that it can find, basically like a tube or a straw, it's going to go up under there and just etch away the copper, and you're going to have an open on your inner layer, and you're going to be very, very disappointed. So quality of your surface is very, very important. Make sure you don't mishandle the copper foil. Inspect it if you have to. If you have poor quality foil, send it back, particularly if you're doing finer lines and spaces. So in summary, like I said, we don't have as much going for us today with dry film photoresist chemistry because they have minimized and they've made significant improvements in the photoresist in terms like exposure and tentability and overall quality operations. They don't use as many adhesion promoter type chemistries to help you. So really, it's up to the fabricator to ensure you have a clean copper surface, you have a reasonably micro roughened copper surface, some topography for the mechanical lock-in, if you will, adhesion, but not too excessive. And then for the lamination side, which again we'll talk about in the future, we want to make sure that the film does conform to the surface, which is again part and parcel to the lamination of the photoresist operation itself.